So now we're going to show you the smart home demo. So it's a demo which focus on both demonstrating the use of the ENACT enablers as part of several DevOps lifecycle and showing their proper integration in DevOps pipeline, and also demonstrating some of the trustworthiness features developed as part of ENACT. So let's start with this demo. So you will see a set of enabler being demonstrated as part of this demonstration. First, use case actuation, conflict management, test and simulation, Genesis, security and privacy control, and behavioral drift analysis enablers. So the scenario in short, so we will start from an existing smart IoT system with already an application already deployed. This application is called User Comfort. It controls luminosity, energy, temperature in the smart home, but also some user routines, such as, for instance, triggering the robot vacuum cleaner at specific time. So, and the objective of our scenario is to augment this smart IoT system by adding a novel application called Communication Center, whose objective is to ensure an acceptable sound level in different situations. And in particular, we will see that we'll try to manage the sound level during phone calls. So, for instance, turning off the TV during phone calls. So these two applications, they are running in app server and they are communicating with all the devices, actuators, sensors in the smart home via the small IoT platform. So even if this smart IoT system looks simple, in reality it's way more complicated than just these few boxes. So it involves quite many software components and the devices. So in terms of numbers, to give you an idea of the complexity of this scenario, so we will deploy and manage more than 81 software components. We will control and interact with more than 50 devices, which mean more than 170 sensors and 70 actuators. We will have 6 edge nodes like Internet box, Raspberry Pis, 4 small nodes, tiny devices without direct internet connection, such as Arduino Unos, Nanos. And all these devices and software components, they communicate with each other via 6 different communication protocol for more or less 570 communication channels. And as I said, in addition, there is the IoT platform small in the picture. So let's start now our demonstration, and let's start with the bootstrap, so the initial application, our user comfort application. And here we should remember that this application has already been deployed using Genesis, so all across IoT edge and cloud devices. It already uses a security and privacy control enabler for a security policy, making sure that only the user comfort app can interact with the devices. And it's already monitored by the behavioral drift analysis enabler, making sure that it is actually effective in reaching its goal. So let's have a look at the application. So the application is composed of several different software components written in different languages, such as Java or here Node-RED. So for instance, these are a set of Node-RED nodes that help building the behavioral logic of the application. So in the end, it looked like a dashboard. This dashboard, so actually it's a set of dashboards. So one dashboard here is for controlling different devices, some dashboard for monitoring. For instance, here it's monitoring temperature and so on. So as I said, this application, this smart IoT system, has already been deployed using Genesis. So here is the Genesis deployment model in Genesis. So we can see that some of the components are surrounded by green boxes. This means they have been successfully deployed by Genesis. If we just right-click on the component called ENACT Producer, it's a component which is it's a small knowledge processor which is used to interact for the interaction between the apps and the IoT devices. And this component, we can see that it is configured with a security policy via Genesis. So it's just a property. And actually, Genesis has automatically generated and deployed the security checker that controls the access from the communication center app to the sensors and actuators. Last, when we can look at the behavioral drift analysis enabler, and we can see on the top of the screen the different context information being monitored, and we can see on the bottom the red graphs are displaying the behavioral drift, and we can see that right now the system is considered as working very fine, the value being at behavior of the drift being at 1. So this was for the bootstrap of our smart IoT system. So now let's increment our smart IoT system. Let's go for our first DevOps loop. So we are trying to add the communication center application, but before we deploy it and put it in production, we need to take a certain number of steps. So first, the application needs to be tested before deployment, and it needs to be tested and with respect to the actual context of the smart IoT system. Since we are adding an application that will also control actuators, we need to check if there will be any actuation conflict between the two applications and if these need to be managed and fixed. Then we will have to update the deployment of our smart IoT system, so redeploy it and also update the security policies, making sure the communication center app can also interact with the sensor and actuators. And finally, we need to test the system again, as a whole. So let's start first by testing our communication center application. So for that, we will use a test and simulation enabler. So important thing that you will see here now as part of this demo is that first, we will see that we have recorded data from the real system, and we will use this data to replay and simulate the smart IoT system. You will see that we can also configure the simulated devices so that they can inject erroneous and malicious data during the test, and this can be simply configured as part of the tool. And we will see how we can build and trigger test campaign and present the result of this test campaign. So let's jump to the test and simulation enabler. So here is the tool. We just launched the test campaign. So as you can see at the bottom of the screen, there are two test campaigns defined right now. We are now triggering the test campaign com center, so the one in bold, which is itself composed of two test cases. So the first one, which is about simply replaying and simulating the system with real data from the real system, replaying recorded data. And the other one is about recording, replaying data and injecting erroneous and abnormal behavior. So let's have a look at this second test case. So we see that we are actually generating erroneous data from 3 different devices. So we can have a look at the type of data being generated from that very device, and how can we configure this generator of erroneous data. So we can just go here in this in this generator, this list of generator, and we will see that each device, our sensors are listed here, and we can edit the behavior of each of these sensors. So if you click on one of these sensors, you see that you can either increase the number of instances, play with the frequency to which you send messages, and you can configure the behavior with select abnormal behavior. So this is how you can generate erroneous data as part of the simulation. So let's have a look now at the result of our test campaign. So we can view the report. So we see that already 2 test cases were passed and are marked as green, while another one is still ongoing. Probably it will be completed in few seconds or minutes. So though the test and the apps is considered as valid, so now we can move to the next step in our DevOps iteration, and the next step is about understanding if there will be any actuation conflict between the two applications. So here for that we will use the actuation conflict management enabler. and we will use it to identify and solve a direct conflict. And in particular, here we will see focus on the conflict related to the management of the TV by the two applications. So here what is important is to understand that this process is, so this tool is adopting a model-driven engineering approach and model-driven engineering techniques. So it leverages a model called WIMAC, which represents the system, and this model is platform and technology independent. So as long as you are able to extract from your system this WIMAC, you will be able to identify and solve your actuation conflict. Here the model that will be considered is pretty large, 2,000 components. And the way we will solve the actuation conflict will be by using an off-the-shelf actuation conflict manager. So a component available, offered by the tool that we will select and that will be injected to solve in the system to solve the conflict. Last but not least, this whole process is working at the model level, is automatic, so it does not require from the developer any modification of the applications. Everything is handled by the tool. So let's have a look at the actuation conflict management enabler. So first we start from a novel deployment model from Genesis, because this is the model that we will use to build this WIMAC model I was mentioning before to identify and solve actuation conflict. So here from Genesis, we have loaded the new model and we trigger checking for actuation conflict. So at some point we will get a notification, here it is, depicting that there are actually actuation conflict. So then we jump to the actuation conflict management enabler to solve this conflict. So we generate the WIMAC model, it will be displayed here, and then we run the conflict identification, find conflict. So a set of conflict will be identified and they will be represented as boxes, tiny boxes, such as this one here. So here now we are going to solve this actuation conflict. So we can zoom in. So here is a conflict related to the TV, as we said before. And actually, as I said before, the way we will solve this conflict is simply by selecting OR component, which will implement OR logic between the two applications. So once this actuation conflict manager selected, the WIMAC model is updated, and we can now deploy the new version of the Smart IoT system. So we will automatically trigger the deployment from the actuation conflict management enabler. So the deployment is triggered. We can see that the deployment is actually ongoing in Genesis. And as you can see, several components are surrounded by yellow borders. So these are the components that are being either added or redeployed in this new deployment. So here, what is interesting to note is that by leveraging the model at runtime approach of Genesis, only the part of the system that needs to be adapted were adapted, so were redeployed. So here, this is the first point that we were interested in looking from Genesis, but another aspect is that actually not only the system was adapted to deploy the new application and inject the actuation conflict manager, but we also have updated the security policy. And just to demonstrate the different capabilities offered by Genesis, this time we have decided to use a third-party security mechanism in order to manage the access from the applications to the devices. So we are using GCASB here. And what is interesting is that again, we don't need to modify the code of the software component, the small knowledge processor that makes the connection between the small and the devices. But Genesis will automatically inject the security code and the code to integrate the third-party security mechanism. So we can have a look at that from Genesis. So basically, we see at the very top here the GCASB component being that has been added, and just below there is an ENACT producer component, which was the component before using the default policy. IoT, the small default policy is now has been changed and configured so that it use and leverage the GCASB security mechanism. So all we do is to provide this property here and a file here, and everything is automatically generated. So we can have a look actually and test this this security mechanism. So meanwhile, we can see that some tests were triggered automatically by Genesis, but we will come back to that later. So first, let's have a look at this new security policy, and let's see if we can interact. The communication center app can interact with the devices in the house. So at the bottom right, you see just a log interface that is showing the messages being received by Small. And here on the camera, we see the smart home and the TV. And here we will just try to send a toast on the TV. We should see on the top right of the TV the toast appearing. Here it is. And we see also in the log that this message, it's actually a message coming from the application and it has been authorized. We could also see at the beginning of the logs that some messages were discarded. Here are the list of messages that were discarded by the security and privacy control. These are messages that we created some fake apps that are trying to access the devices. And these are trying to send the messages, but these messages are discarded. So the system is deployed, and we are able, the two applications have access to the devices. So as we said, once the deployment from Genesis was completed, a set of tests were automatically triggered by Genesis. No. So they were automatically triggered as part of the DevOps pipeline. So this is one of the key takeaways, and we will see the result of this test just now. And again, this test, as the former one, they are replaying real data, and they are also injecting not only anomalous and erroneous data, but they are also simulating security attacks. So here are the result of the three tests. So same as before, we have defined the test campaign and the data generator and so on as we did before, but this time we also tested security aspect. So now we consider that our system is actually working. Tests were successful. So let's play a bit with our Smart IoT system. So here is again the smart home, and let's see actually if our actuation conflict management solution is working very fine. So we are trying to trigger a phone call, and this phone call should mute the TV, and we can see actually here on the right of the TV that the TV is muted. We should also see that the application, the user comfort application, is not able to unmute the TV. So the TV remains muted. So it seems the actuation conflict management is working fine. So let's see if we can trigger maybe some other action. So typically, normally at this time, the robot vacuum cleaner is also triggered automatically by the user comfort application. So let's trigger the robot. Here we go. It's running. We can see it. Moving. So it seems everything is working fine. So now our system is in production, but of course we should monitor our system to understand to which extent it is effective. So let's have a look at our behavioral drift analysis enabler. And actually we see that when it comes to the noise, we see a huge drift. So basically the drift value has moved from 1, so perfect, to 0, showing there is a problem. So there is actually at some point a drift when it comes to the management of the noise in the house. So okay, we need to understand what is this, where is this coming from, and how we can solve this issue. So to understand where this drift is coming from, we will use a behavioral drift analysis enabler. So not only looking at the drift value, but trying to analyze this drift. And second, we will update the Smart IoT system to fix this issue. So first, we will use the behavioral drift analyzer to analyze the system. So far we were continuously computing the drift. Now we will try to understand in which state the system has been, which was a state unexpected from the development perspective. So let's have a look at the behavioral drift analysis enabler. So here is the simplified version of the behavior expected for the management of the sound. So let's now run in the analysis mode. So we load this behavioral model, so the model of the expected behavior of the system. So this it's represented as a finite state machine. So all the green state are the expected state. Then we load data from the system when working fine, as expected. And we load data from the system when working in unexpectedly. So and we can trigger the analysis. So we will see on the right of the screen the result of the analysis. And in a more user-friendly way, we can see in the final state machine that a new state has appeared. It is depicted in red. And basically, what he said is that at some point, there was a phone call, but still the sound level was very high. So the reason for that is pretty simple. It's because usually the robot cleaner is configured, and the routine is configured to trigger the robot cleaner during working hour because no one is at home. But now, with the change of situation due to COVID, basically the robot has been triggered while there was a phone call at home for a meeting. So this is a situation that could not have been anticipated at the origin and in the original design of the system. And actually, this is a situation that is resulting from an actuation conflict, an indirect actuation conflict. So let's go back to the slide first. All right. So actually, this conflict is an indirect actuation conflict. So it's coming from the time that one application is triggering the robot vacuum cleaner, which make a lot of noise. And the other one is trying to stop all the noise except the one from the phone call to make sure the phone call is going fine. And then we see that the noise is this physical phenomenon where two actuators are that is impacted by two different applications and via two different actuators. So it's an indirect actuation conflict. So we will use actuation conflict manager to solve this conflict. To do that, we will show that we can refine the description of the physical environment of the smart IoT system. So here we will depict the fact that actually the robot can have an impact on the noise in the room. And this time, to solve this indirect actuation conflict, instead of reusing an off-the-shelf actuation conflict manager, we will use a custom actuation conflict manager. So custom actuation conflict manager is an actuation conflict manager designed, specified by the DevOps team. This actuation conflict manager is specified using a domain-specific language that has been defined for the enabler, and each of the custom actuation conflict manager are also checked against some logical and temporal properties, making sure that the management of the actuator is safe. So let's have a look now at the actuation conflict management enabler. So here is again our ENACT model. So we can go for identifying a conflict. So let's first modify the physical the model of the physical environment. So saying that the robot will impact the noise in the living room. Once we have refined our ENACT model, we search again for conflict. And a new conflict will be identified. So we can see on the top left that there is one unconfigured actuation conflict manager. So here is a list of actuation conflict manager, and here is the one that we need to solve, the remaining one, the new one. So here it is. We will solve it, and this time, instead of selecting an off-the-shelf actuation conflict manager, we select the form for creating your own custom actuation conflict manager. So we will write the behavior of this manager using the ECA Plus domain-specific language. And then we check this actuation conflict manager against semantic and temporal properties. So it seems now the check has been, everything is okay. So the actuation conflict management component manager has been generated, and it will be injected automatically as part of the system. So to do that, we redeploy the Smart IoT system directly from the actuation conflict management enabler. So once again, the deployment is triggered. Only the part of the system that needs to be updated are updated. So for instance, here this time we see that the security components are not updated anymore, and the new deployment is completed. So let's now test our new Smart IoT system. So let's go in the smart home. So we see that the robot is still going on. Here we can see it next close to the TV. And let's try to trigger a call and see if the robot is automatically stopped. So we see the TV was muted, and we see the robot is paused, so it should be behind the sofa. So our actuation conflict management has worked successfully.